Greetings to all and welcome to this lecture. We are in module 4, lecture number 2. So, we will discuss small signal capacitance in more detail. In this lecture, we will see what is the minimum capacitance and what is the slope factor. These are the learning outcome of this lecture, which helps us to understand thoroughly about the small signal capacitance of two terminal MOS structure. Let us do a quick recap. In previous lecture, we have discussed that the two terminal MOS structure given by this having a metal, oxide and semiconductor, when you change the gate to body voltage, that change is reflecting into the change in channel charge, and hence there will be overall capacitance comes into picture. This capacitance is nothing but gate to body capacitance. 1 over CGB dash is nothing but 1 over COX dash plus 1 over CC dash. So, we discussed that the overall capacitance of this two terminal MOS structure is nothing but the series combination of this oxide capacitance and this channel capacitance. We argued on calculation of CC dash, which is nothing but minus of differentiation of channel charge with respect to surface potential, and we said that this minus term does not mean the capacitance is negative, rather to make the capacitance positive we are taking a negative direction. Finally, we concluded the closed form equation of CC dash, which was CC dash is equals to signum of psi s square root of 2 into q into Na into epsilon s 1 minus e to the power of minus psi s by phi t plus e to the power of minus 2 phi f by phi t into e to the power of psi s by phi t minus 1 divided by 2 times square root of phi t e to the power of minus psi s by phi t minus phi t plus psi s plus e to the power minus 2 phi f by phi t into e to the power of psi s by phi t into phi t minus psi s minus phi t. So, this expression is nothing but the derivation of QC dash, which was we defined earlier, which is a channel charge. This channel charge is can be given by a contribution of holes, electrons and immobile ions. Likewise, we derived the complete form of CC dash. Then we classified CC dash in various regions of operation, considering accumulation, depletion and inversion. We use some good amount of approximation to ignore the term which are having negligible significance. Like in accumulation, when surface potential is negative, and if we talk about deep in accumulation, then surface potential is very much negative, and hence this term dominates, and other terms will not dominate, because this term, if you remember, it is given by electron contribution. Similarly, in denominator, this term is given by electron contribution, this term is given by immobile ion contribution. Likewise, we calculated a form of channel capacitance CC dash for deep in accumulation, depletion and inversion. And finally, we concluded that in deep in depletion and inversion, these total capacitance are in parallel. It means CB dash and CI dash are in parallel. So, it is like you have a total capacitance between gate to body is a series combination of COX and CC dash, where CC dash is a parallel combination of CB dash and CI dash, where CB dash is the capacitance due to bulk and Ci dash is the capacitance due to inversion layer. We have discussed also about the overall CB characteristic, in which we plotted the capacitance of two terminal MOS with respect to the gate to body voltage, and we found the figures something like this. Let us explore this in more detail. So, let me plot the CV characteristic step by step. So, this is gate to body voltage and this is total CGB dash, which is the small signal capacitance of your MOS structure. Now, the maximum possible capacitance is nothing but COX dash, because remember that CGB dash is nothing but a parallel combination of COX dash and CC dash. In various regions of operation, when CC dash varies, accordingly the value of CGB dash can be fixed, but it will not exceed beyond COX dash. So, let us start with accumulation. In accumulation, what will happen? Your VGB is negative. If VGB is negative, then surface potential is negative, and if the surface potential is negative, we have just seen that the CC dash in accumulation can be given by square root of, so CC dash in accumulation can be given by square root of, so it is Q into epsilon S into Na divided by 2 times of phi t e to the power of minus psi s by 2 phi t. So, it is an exponential dependency with respect to surface potential. That is what when the surface potential is very much negative, CC dash is very much high. If CC dash is very high, then what will happen about this term? It is very low, and hence CGB dash approaches to COX dash. So, we will start with this region of operation, and this is accumulation. So, this region I am defining as accumulation. Now, there is a condition of VGB which is called as flat band condition, when there is no charge available into it. Again, we discussed in previous lecture that though there is no charge in the semiconductor surface, but we cannot say that there is no capacitance, because capacitance is not charge per voltage, it is change in charge per voltage. And hence, we have also found using L'Hopital's rule that when psi s is equals to 0, meaning you are in flat band condition, there is a capacitance exist, and that capacitance value was square root of Q times epsilon s into Na into 1 plus e to the power of minus 2 phi f over phi t divided by phi t. And this capacitance having some significance number or significance value, which we need to come here, and hence if CC dash is lower than this value, ultimately you have CGB dash having a decline trend. So, from accumulation to flat band condition, you have a decline trend, and we can see that this decline trend is somewhat exponential, because exponential of minus psi s by phi t dependency. So, in this region of operation, we can use our MOS structure as a varactor. Varactor means a voltage dependent capacitor. Now, let us go and increase the VGB towards positive direction. So, for the sake of simplicity, let me make a 2 terminal structure. Here we are applying VGB, this is metal, this is oxide, and this is semiconductor. So, when you increase VGB, what will happen? Initially, the positive VGB will repel the hole towards the body. So, hole will go towards the body, and hence immobile ions will come. If the immobile ions will come, there will be a capacitance which is what? CB dash. And we have seen that CB dash is given by this, which is approximately proportional to 1 over 2 times of square root of psi s. And hence, this CC dash is converted into CB dash. So, overall CGB dash till depletion can be given by 1 over COX dash plus 1 over CB dash. as the depletion thickness increases, the overall capacitance will reduce. So, you have a decline trend till flat band. This is VLO. So, VLO is the voltage of VGB corresponding, the surface potential is what? Phi f. So, in this psi s is equals to phi f. So, you are in depletion. Now, beyond depletion, if you further increase VGB, more positive charge will come into the gate, and hence more number of negative charge is required at the surface. So, first of all, what will happen? Some more immobile ions will be uncovered, and then a few inversion charge will come into the surface. So, this will happen till VMO, which we define the gate to body voltage corresponding to which surface potential is equals to 2 phi f. So, this decline trend of capacitance continues till VMO, but not exactly at VMO. So, it is like just before 2 phi f value. But what will happen just after 2 phi f? The surface potential becomes 2 phi f. So, the inversion charge having an exponential dependency. If the inversion charge having exponential dependency, we have seen that Ci dash is also having an exponential dependency of charge, exponentially dependency of surface potential. So, we will get immediately rise in the capacitance after 2 phi f, and again this Cc dash is increasing to a very high value. If Cc dash is increasing to a very high value beyond 2 phi f, this term can be negligible. So, ultimately 1 over Cgb dash is approximately equal to 1 over Cox dash, which means my gate to body capacitance approaches to Cox. This is in inversion. So, let me define another term VHO. We call this is an onset of strong inversion, and this is moderate inversion, and this region is weak inversion. So, this trend is coming out as a CV characteristic of a MOS structure. Let me give you an analogy. We have considered this analogy earlier also. Now, let us retake that analogy and add some additional stuff to understand the CV characteristic of a two terminal MOS structure. Let us consider a piece of land, and you want to dig a pit on that piece of land. So, what you are doing? You are actually shoveling the soil out of it, right. So, removing the soil from the surface is nothing but similar as removing the holes from the surface. So, consider this piece of land is equivalent to MOS structure, and you are applying a force or work done to remove the soil. That is what same as you are increasing VGB. Initially, what will happen? The holes will be removed from the surface, and hence uncovered immobile ions will come up. This immobile ions is similar as the depth of this pit. Now, what will happen if you apply more work done? If you remove the soil further, the depth of pit will increase. Similar as if you increase VGB, the depth of depletion region will increase. You can consider, and after that what will happen? If you further increase the height of this pit, there is a possibility that the groundwater will leak through this hole and come to the surface. This groundwater analogy is similar as the inversion charge will come towards the surface, right. This analogy we have already discussed. Now, you consider a add-on in this analogy is like you have another plate. So, it is like you are taking a top plate and this is your ground. So, you want to measure the distance between the top plate and the ground. So, this is you have a top plate. Consider this top plate as a top plate of a capacitor, and consider this land, piece of land, as a bottom plate of the capacitor. and go with a similar analogy that capacitance per unit area can be given by epsilon divided by d. It means if the distance between the plate will increase, then the capacitance will decrease. Now what will happen if you first remove the soil from the land? So the distance, effective distance between the plate and the land is this distance plus the height of the pit, and hence the overall distance between that top plate and the bottom land is actually the top plate plus the height of the till the height of land plus the pit height. So ultimately d will increase. If d will increase, the capacitance will decrease. That is what we are actually getting, a decrease in the capacitance in depletion region. Here if you use that same analogy, when you are applying VGB, the depletion region coming into picture, so the overall capacitance or the distance between the plates of the charge separation will increase and the capacitance will decrease. But what will happen beyond a certain point? Beyond a certain point, the water will come from the ground and fill that pit. So the minimum distance is nothing but the top plate till the water level. That distance is again reduced, and then the capacitance will again increase because the distance is reduced, the capacitance will increase and it reaches to the COX value. The same thing is happening here. When you increase VGB, then the inversion charge will come near the surface, and these inversion charge will form a charge available in the lower plate. So the overall height is nothing but effectively TOX. Strictly speaking, the inversion layer charge having some amount of thickness, thus the capacitance here will be lower than COX. So we can say the capacitance in the inversion approaches to COX, it will not become exactly equal to COX. So this is what we have discussed so far about CV characteristic of a two-terminal MOS structure. But we have untouched one aspect is about this region. What will happen at 2 phi f? So when you are talking about deep in inversion, then at that moment the height of the depletion region is maximum. If the height of the depletion region is maximum, and beyond the, after that maximum height, what will happen? The inversion charge will come. So when the height of the depletion region is maximum, your overall capacitance is minimum. So let me define a minimum capacitance as CGBL. L stands for lower. So this minimum capacitance can be obtained here. This is the minimum possible value of CGB dash. How can we calculate this minimum capacitance value? So again we will use our understanding that we are actually saying that my MOS structure will have the maximum depletion thickness when we are in strong inversion. So you are applying VGB and you are considering that my maximum depletion thickness is dBm. I think we have already discussed in previous lectures dBm. So this dBm is correspond to surface potential value of 2 phi f plus phi z0, which we termed it as phi naught. So at that surface potential we will get the maximum depletion thickness. So we can simply say 1 over CGB dash is equals to 1 over COX dash plus 1 over CB dash. Means CB dash you can add another subscript L, which says that the lowest possible CB dash correspond to the maximum depletion thickness. So if you solve this, it will CB dash CBL dash into COX dash divided by COX dash into CBL dash. This is the value of 1 over CGB dash. So CGB dash, equivalent gate to body capacitance per unit area, is given by COX dash CBL dash divided by CBL dash plus this is plus COX dash. take CBL dash common, you will get COX dash divided by 1 plus COX dash by CBL dash. Now, can we calculate the CBL dash from this understanding of maximum depletion thickness? We know that the charge in this condition can be given by QB dash, which is nothing but minus of 2 into Q into Na into epsilon s into root psi s. Here we need to replace this psi s by phi naught, which is nothing but 2 phi f plus phi z0 when you are talking that you are in strong inversion. So, if we do the differentiation to calculate CB dash, then with a negative sign, remember that negative sign is to make the capacitance positive. This will give you CBL dash. So, you can differentiate, this will give you square root of 2 into Q into Na into epsilon s divided by 2 times square root of phi naught. Now, you put here and ultimately CGB dash L, the lowest possible capacitance, the overall capacitance between gate to body terminal can be given by COX dash divided by 1 plus COX dash into square root of 2 into Q into Na into epsilon s 2 into square root of phi naught. This is a known quantity. This quantity is called body effect coefficient, gamma. So, gamma is nothing but 2 into Q into Na into epsilon s divided by COX dash. So, I can get a complete equation for CGB dash, which is lowest possible capacitance in the MOS terminal, in the 2 terminal MOS cap, is COX dash divided by 1 plus 2 by gamma into phi naught. So, this is the final expression what we got for 2 terminal MOS cap, which says that the minimum capacitance exists after this VMO point, because we claim that after this VMO point we will go in strong inversion. Let me conclude this CV characteristic with one more additional point, that this dotted line shows the CV curve for high frequency of operation. Whatever we have discussed, you discussed for a quasi static or steady state condition, meaning you applied a VGB, the VGB will add some additional charge into the gate and the gate will causes a negative charge into the surface. So, this process takes time and hence you are giving time to the charge to respond. That is what you are having CV characteristic like that. But what will happen if you connect a AC signal in your MOS cap and you are increasing the frequency? If the frequency is very high, then beyond depletion you are not giving time, enough time to the inversion charge to come from the body to the surface, and hence you will get the capacitance stays at lower value, because the overall capacitance in that condition also was given by 1 over CGB dash is equals to 1 over COX dash plus 1 over CB dash. But we will see in subsequent lectures that when this MOS 2 terminal MOS will become a part of MOSFET, then this dotted line can go up, because we will connect the inversion layer with an external environment. Let us see much more about the capacitance and the relation between surface potential and the inversion charge. We will define a slope factor which is n. You remember in weak inversion we define a slope factor n, and we said that slope factor is a factor which actually tells you how much gate control you have over surface. So, we have defined the slope factor n as d psi s by dVGB inverse. So, if we see the surface potential versus VGB graph, we found that it is linearly rising and after that it gets saturated. So, here the slope is almost linear and after a point 25 f, which we called it as onset of moderate inversion, here the surface potential starts to pinned. Let us do some mathematics and use our basic potential balance equation, which is VGB is equals to phi ms plus psi s plus psi ox to calculate this slope, which means d psi by dVGB inverse. If I will replace psi ox phi ms plus psi x plus qg dash by cox dash. In this condition, this qg dash is nothing but what? Minus of qc dash over cox dash. Now, again this channel charge can be split into two parts, one is inversion charge and one is bulk charge or body charge. So, if I rewrite this equation as VGB equals to phi ms plus psi s minus, so we missed one term which is q naught dash also, which is oxide charge. So, minus q naught dash by cox dash minus qi dash plus qb dash divided by cox dash. We remember and we are familiar with this term. This is nothing but flat band voltage plus psi s minus qi dash plus qb dash divided by cox dash, which is nothing but equal to VGB. Now, we are interested in to calculate the slope, meaning d psi by dVGB. So, let us differentiate this equation with respect to VGB. We will get 1 is equals to the differentiation of flat band voltage with respect to VGB 0, because flat band voltage is constant for a particular value of work function and the oxide charge. So, this is 0 plus, as you are differentiating this equation, let us say equation number 1 with respect to VGB, you will get delta psi s by delta VGB minus, or to get its simplification I am writing plus with minus of dqi dash plus dqb dash divided by dVGB over 1 over cox dash. Now, if we do some further simplification, you will get d psi by dVGB. This can be written as plus 1 over cox dash and this can be written as minus dqi dash by d psi s plus minus dqb dash by d psi s into d psi s by dVGB, because these are the known quantities to us. This is nothing but Ci dash, this is nothing but Cb dash. So, let us simplify it. 1 is equals to d psi by dVGB, I am taking it common. You will left with 1 plus 1 over cox dash into Ci dash plus Cb dash. If I am going to calculate d psi by dVg, it is d psi s by dVGB is equals to cox dash divided by cox dash plus Cb dash plus Ci dash. So, this is this quantity what we have extracted here using a simple potential balance equation. Now, let us do and calculate some slope of the known graphs between surface potential and VGB and finally the charge and the VGB. We know that the slope of this charge and VGB is important because it tells us in which region of operation we are. So, dq by dVGB, if we are interested, it means we are interested to find out the slope of this graph, is can be written as d into qi by d psi s and d psi s by dVGB. This quantity is again nothing but Ci dash. Remember, here we are plotting the mod of Qi, and hence we need not to bother about the negative sign. And this quantity we just calculated as Cox dash divided by Cox dash plus Cb dash plus Ci dash. So ultimately what we are doing, we are actually trying to relate all the graphs which we have calculated, like surface potential versus VGB or charge versus VGB, which tells us how surface potential and charge are related with the external voltage in terms of capacitances. Because if we know the capacitance, then we can simply extrapolate those analysis to find out how much good gate control do you have. Similarly, you can find out the slope of log of Qi and you will get this. Let's explore further about this slope factor, because when we are going to discuss about the MOSFET, then in subthreshold conduction this slope factor will come again and again. So what we said is this N is nothing but d psi by dVGB inverse, and in the previous slide we have calculated d psi by dVGB is equals to Cox dash divided by Cox dash plus Ci dash plus Cb dash. But the slope factor, the ideality factor, we talked in weak inversion. So in weak inversion you do not have Ci dash, because the charge is predominantly governed or captured by immobile ions. So you can simply rewrite for weak inversion, this can be given as Cox dash divided by Cox dash plus Cb dash. This is nothing but d psi s by dVGB. We simply ignored Ci dash, right? Now the inverse of this is nothing but what? N. So N is nothing but 1 plus Cb dash divided by Cox dash. This N tells us how much good control do you have. Now you have a parameter which is considered as capacitances, with which you can define the gate controllability in weak inversion. I will give you another simplification to solve this. Let us consider you have a two terminal MOS structure like this. This is metal plate, this is oxide, and this is semiconductor. So here you have oxide, let me make like this, you have an oxide, and this is channel charge Qc dash. This channel charge in weak inversion is given by Qb dash. It's similar as you have two capacitances in series. So what you are doing, you have one capacitance which is considered as Cox dash, and you have another capacitance which is considered as a body capacitance Cb dash, and you are applying the gate to body voltage in this configuration, gate to body voltage VGB in this configuration where two capacitances are in series. You want to calculate what is the surface potential. So you see the surface potential will come across this region, right? It means it will come across Cb dash. So if I am interested what is the change in surface potential, you can simply use a potential balance equation, or you can simply use a voltage divider equation. Voltage divider in capacitor means dVGB into, you need to take this capacitance Cox dash divided by Cox dash plus Cb dash. So ultimately you will get the same equation what we have derived from our basic potential balance equation, delta psi by delta VGB is equals to Cox dash divided by Cox dash plus Cb dash. Let us do a small analysis further, that what is the capacitance offered by interface trap charge. You remember that in a first lecture we said that Q naught dash is fixed. It means we are considering the oxide charge is fixed. It is not varying, and we consider that it will be considered as positive always. However, in some cases there is a chance that interface trap charge vary with voltage, meaning whenever you are writing the potential balance and charge balance equation, you need to consider that QIT as a function of voltage. So, if I rewrite the equation of potential and charge balance, VGB is equals to phi ms plus psi s plus psi ox. This is a potential balance equation, and the charge balance equation now it will be Qg dash plus Q naught dash plus Qc dash plus Qit dash is equals to 0. So, we just considered that the interface charge are separate than the oxide charge. There are few types of oxide charge. We consider that oxide fixed charge, oxide trap charge, mobile ionic charge. So, this will be considered in this group like Q naught dash, but we considered separately as interface charge. So, when you are taking a change in these values, so delta VGB is equals to delta of psi s plus delta of psi ox, but when you take the change in gate charge, you need to consider that trap charge will also change. Earlier, we were only considering the change in the gate charge is actually reflecting the change in the channel charge, but you need to consider here that change in the gate charge will reflect in the change in trap charge, because the trap charge is controlled by the applied gate voltage. So, if you rewrite this potential balance equation and charge balance equation, you will come to VGB is equals to phi ms plus psi s plus Qg dash divided by Cox dash. So, I replace this psi ox by Qg dash by Cox dash, and now it can be written as phi ms plus psi s minus Qc dash minus Qit dash divided by Cox dash Cox dash. So, in this condition, if you calculate with the same approach, you will get there will be a term coming out dQit divided by d of psi s. This term is defined as the capacitance due to traps, and when you calculate the slope factor n, that n can be given by 1 plus Cb dash plus Cit dash divided by Cox dash. So, let me summarize this. So, in this lecture we have discussed a small signal equivalent capacitance of two terminal MOS structure. We said that in various region of operations our CV characteristic looks like this. It approaches to Cox value in inversion, but not becomes exactly equal to Cox. It is equivalent to Cox or approaches to Cox in accumulation, and it will find the minimum after 2 phi f. We have also calculated the minimum capacitance, which was given by Cgb dash L is equals to Cox dash divided by 1 plus 2 by gamma square root of phi naught, where phi naught is the surface potential when you are in strong inversion. After that, we have also seen that there is a provision now we can define the gate controllability on the surface charge or on the surface potential in terms of capacitances. So, we define the slope factor d psi s by dVGB as Cox dash divided by Cox dash plus Ci dash plus Cb dash. With this slope of surface potential with respect to VGB, we said that we can define the slope of other relations like Qi dash and VGB, and we found that delta Qi dash divided by delta VGB can be defined as delta Qi dash divided by delta psi s into delta psi s divided by delta VGB, where this is per unit area. Finally, we said that under weak inversion the slope factor n can be defined as 1 plus Cb dash divided by Cox dash. It means if you know the capacitances in the depletion and if you know the capacitance of the oxide, you can simply find out what is d psi by dVGB, and this tells you how much good control of your gate on your surface charge or on your surface potential is. So, we will stop here for today. Until then, take care.